Now we introduce the quantity energy density little u, which is the energy in a field per unit of volume. It will have the units joules per cubic meter. The energy density for an electric field, U sub E, is equal to a half E naught times E squared. The energy density U sub B of a magnetic field is U sub B equals 1 over 2 mu naught times B squared. So, since for electromagnetic waves, electric and magnetic fields vary with time, the energy densities of those fields also vary with time. Let's show that the energy density in the magnetic field is the same as the energy density in the electric field. So we remember that B equals E over C, and C is 1 over root mu naught E naught. So just starting with that expression for UB, B squared over 2 mu naught. We substitute in that is E over C squared over 2 mu naught, and that C squared equals 1 over mu naught E naught. So we end up with the expression for the energy density in the magnetic field is a half E naught E squared, which is equal to the energy density in the electric field that we were given up the top. So we get UB equals UE. This is saying that the instantaneous energy density in the electric field equals the instantaneous energy density in the magnetic field, and that is always true. So in any volume of space, the energy is always going to be equally shared by the two fields. So if we want to get the total energy density of an electromagnetic wave, we just add UE and UB up to get the total energy density, which is E naught E squared, or we could write it as B squared over mu naught. This is instantaneous because it is changing with time as the electric and magnetic fields change. So once again, we take an average. We average the energy density over one cycle of the wave to get the average U. And E and B being sine functions and U being proportional to sine squared, we know that the average of the sine squared function is 1/2. So that gives us the expressions at the bottom for U average in terms of electric field and also in terms of magnetic field. Now we want to relate energy density to the intensity of the field. We saw how the intensity was related to the amplitudes of the electric and magnetic fields E and B. These expressions look quite similar to the ones for energy density. In fact, if we take the energy density equations and multiply them both by C, we find that they equal the equations for intensity, as long as we remember that C squared equals 1 over mu naught E naught. So we end up by finding quite a simple equation that I, which is the average of the Poynting vector, is C times the average energy density. That's summed up in the sentence at the bottom. The intensity of an electromagnetic wave equals the average energy density multiplied by the speed of light.